Hello there, and welcome to the Sleepy Facts channel. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to the gentle mysteries of the deep rather than counting sheep. Either way, tonight's journey is for you. Let your mind relax, your breathing slow, and your body grow light as if drifting through calm blue waters. Because tonight, we're exploring sharks, creatures far more peaceful than their reputation suggests, gliding through the ocean with a grace refined over 400 million years. We'll drift from their ancient origins to their surprising gentleness, discovering that most sharks are quiet, slow-moving beings that pose no threat to humans. Some of what you hear tonight may surprise you, or at least spark curiosity as you drift off. Before we begin, if this helps you unwind, consider liking and subscribing, one sleepy soul at a time. Now, let's begin. Sharks are among the oldest creatures on Earth, having existed in the oceans for over 400 million years, long before dinosaurs walked the land or trees grew in forests. They have survived 5 mass extinction events that eliminated most other species, persisting through catastrophes that reshaped life on the planet. Their longevity speaks to a body plan so successful, so perfectly adapted to ocean life, that it has required little fundamental change across geological ages. The shark, swimming through today's ocean, is not dramatically different from sharks that swam through ancient seas, when the continents were arranged in configurations we would not recognize. They are living connections to deep time, creatures whose lineage stretches back so far that human history becomes merely the most recent moment in their story. These ancient fish belong to a class called chondrichthyes, meaning their skeletons are made entirely of cartilage rather than bone. Cartilage is lighter and more flexible than bone, giving sharks advantages in buoyancy and movement, allowing them to glide through water with minimal effort. The cartilaginous skeleton also means that sharks rarely fossilize completely, their soft skeletons decomposing while only their teeth, which are constantly replaced throughout their lives, survive to become fossils. These scattered teeth, found in rocks around the world, provide glimpses into shark history, evidence of species long extinct and ecosystems vanished millions of years ago. The shark is built of material that disappears after death, leaving behind only the hardest parts, teeth as numerous as days in their long lives. The shark's body is covered not in scales like other fish, but in dermal denticles, tiny tooth-like structures that give shark skin a rough texture if stroked the wrong way. These denticles are arranged in overlapping patterns that reduce drag as water flows past, creating a surface so efficient that engineers have studied it to design faster swimsuits and more efficient aircraft. Each denticle is shaped to channel water in ways that minimize turbulence, the entire skin becoming a fluid dynamic surface that allows the shark to move through water with remarkable efficiency. The texture that seems rough to touch is actually sophisticated engineering, evolution's solution to the problem of moving large bodies through resistant water. This streamlined efficiency extends to the shark's overall body shape, which in most species follows a fusiform design, tapered at both ends, thickest in the middle, cutting through water with minimal resistance. The body is neither perfectly symmetrical nor randomly shaped, but rather follows curves and proportions that physicists recognize as optimal for moving through fluid. The shark did not calculate these shapes but arrived at them through millions of years of selection, bodies that moved efficiently, surviving and reproducing while less efficient forms gradually disappeared. What remains is a form so refined that it seems almost designed, though the designer was simply the relentless testing of survival across countless generations. The shark propels itself, primarily through side-to-side movements of its body and tail, waves of motion traveling from head to tail, pushing against the water and driving the shark forward. The tail fin, called the caudal fin, provides most of the thrust, its shape varying between species depending on swimming style and speed requirements. Fast-swimming sharks have lunate tails shaped like crescents, efficient for sustained high-speed travel. Slower sharks have asymmetric tails with elongated upper lobes that provide lift and maneuverability at low speeds. Each tail design suits particular lifestyles. Fast hunters getting speed, while slow bottom dwellers get precision. Evolution distributing solutions according to need. Beyond the tail, sharks possess several other fins that provide stability and control. The dorsal fin on the back prevents rolling, keeping the shark upright as it moves. Pectoral fins near the front act like airplane wings, providing lift and allowing the shark to rise or descend in the water column. Pelvic fins near the rear provide stability and assist with maneuvering. Together, these fins allow sharks to move with precision through three-dimensional space, maintaining position in currents, hovering motionless when desired, or executing tight turns when necessary. The shark is not merely pushed forward by its tail, but actively controlled by multiple surfaces working in coordination, a living submarine navigating through liquid space. This leads to something even more remarkable about how sharks maintain buoyancy without the swim bladder that most bony fish use. Instead, sharks rely on large, oil-filled livers that provide buoyancy, the oil being less dense than water, and thus helping the shark float. A shark's liver can account for up to 30% of its total body weight, an enormous organ that serves both as buoyancy, control, and energy storage. The liver's oil composition varies between species and can be adjusted over time. Sharks modulating their buoyancy by changing liver oil content and composition. This system is more flexible than a swim bladder and does not create problems when the shark changes depth. No risk of overexpansion or rupture that swim bladders face during rapid depth changes. While the liver provides buoyancy, the shark must still swim continuously to maintain position and to breathe. Most species lacking the ability to pump water over their gills while stationary. This creates a life of perpetual motion. Sharks swimming always, even during rest, their bodies moving forward while their brains partially sleep in patterns similar to those of whales and dolphins. The motion is not frantic, but measured. A steady forward glide that requires less energy than one might imagine. The efficient body shape and smooth skin, minimizing resistance. The shark becomes a being defined by movement, existence as continuous travel, stillness achieved not through stopping but through slow gliding, motion so smooth it approaches tranquility. Not all sharks require continuous swimming. Some species, including nurse sharks and wobbegongs, can rest on the seafloor, pumping water over their gills by opening and closing their mouths, a behavior called buccal pumping. These bottom-dwelling sharks live more sedentary lives, lying among rocks or in caves during the day, emerging at night to search for food. Their lifestyle is fundamentally different from the perpetual swimmers, more like that of ambush predators that wait for opportunity rather than actively seeking it. The diversity of shark lifestyles demonstrates that being a shark does not demand any single behavior pattern. Evolution, exploring multiple ways to be successful within the shark body plan. Among the most peaceful sharks are the filter feeders, enormous, gentle species that consume some of the ocean's smallest prey. The whale shark, largest fish in the ocean, reaches lengths of 12 meters or more, but feeds primarily on plankton, tiny drifting organisms that it filters from the water in massive gulps. Swimming slowly with mouth agape, the whale shark processes thousands of liters of water through its gills, straining out the small creatures while the water flows through. This feeding method requires no aggression, no hunting skill, merely the patience to swim through areas where plankton concentrates, opening one's mouth and letting physics and biology do the work. The whale shark is enormous, but harmless, a giant that poses no threat to anything larger than a shrimp. The basking shark, second largest fish species, feeds in similar fashion, cruising slowly through plankton-rich waters with mouth wide open, filters in its gills catching tiny prey while water flows through. Basking sharks often swim at the surface, their tall dorsal fins and tail tips visible above water, creating sights that sometimes cause alarm, until observers realize these giants are harmless, interested only in the microscopic soup through which they swim. Watching a basking shark feed is witnessing patience made physical. A massive creature moving with dreamlike slowness, taking whatever the ocean provides, asking nothing more than that the water contains enough small life to sustain its bulk. The megamouth shark, discovered only in recent decades and rarely seen, is a third filter-feeding species, living in deep water and migrating vertically to follow plankton layers that rise toward the surface at night and descend during the day. Fewer than 100 megamouth sharks have been observed or documented, making it one of the least known large animals on Earth. Its existence remained unknown to science until the late 20th century. A creature weighing hundreds of kilograms swimming through the ocean unnoticed by humanity. A reminder that the ocean still holds secrets, that even large animals can remain hidden in the vast blue spaces that cover most of our planet. Beyond these filter feeders, many other sharks pose little or no threat to humans, living their lives in ways that rarely bring them into contact with people, or feeding on prey too small to include anything as large as a human. The leopard shark, a small spotted species found in shallow coastal waters, feeds on crabs, shrimp, and small fish, spending much of its time resting on sandy bottoms. The horn shark, with its distinctive horn-like projections above its eyes, hunts invertebrates along rocky reefs, moving slowly and deliberately, more likely to flee from divers than to show any interest in them. The angel shark lies buried in sand with only its eyes exposed, waiting for small fish to pass close enough to catch, posing no danger to anything larger than its prey. While these peaceful species make up the majority of shark diversity, their existence is often overshadowed by the few species that occasionally interact with humans in ways that attract attention. Yet even among the species considered dangerous, actual encounters are rare, and the shark's behavior is typically not aggressive but exploratory or defensive. Sharks lack hands to investigate objects, so they use their mouths, taking exploratory tastes of things they encounter. When a shark investigates a swimmer or surfer, the shark is often simply trying to determine what this unfamiliar object is, not attempting to feed. Most such investigations end with the shark swimming away, having determined that the human is not its normal prey. This exploratory behavior reflects the shark's intelligence and curiosity, traits often overlooked when sharks are portrayed as mindless eating machines. Sharks have relatively large brains for fish, and some species show problem-solving abilities and learning capacity that rivals that of some mammals. They can be trained. They remember specific locations where food is found, and they modify their behavior based on experience. A shark that encounters a human and finds the experience unrewarding learns from that encounter the lesson carried forward to guide future decisions. The shark is thinking, processing information about its environment, making choices based on understanding rather than pure instinct. The shark's senses, refined over hundreds of millions of years, allow it to perceive its environment in ways that seem almost supernatural. Sharks can detect electrical fields produced by living creatures, sensing the tiny currents generated by muscle contractions and nerve impulses. This electroreception operates through organs called ampullae of Lorenzini, jelly-filled pores scattered across the shark's snout, each pore containing sensory cells that respond to electrical gradients in the water. A shark can detect a fish buried in sand by the electrical field its body produces, can sense prey hidden from sight and smell, can navigate by sensing the Earth's magnetic field. They perceive a dimension of reality invisible to humans, sensing what we cannot, experiencing the world through senses we can barely imagine. Beyond electroreception, sharks possess exceptional smell, able to detect certain substances at concentrations as low as 1 part per million. The shark's nostrils are not connected to its respiratory system but are solely dedicated to smelling, channeling water past olfactory tissue as the shark swims. Much of the shark's brain is devoted to processing smell, this sense being among its most important for finding food and navigating. A shark can detect the scent of prey from considerable distances, following concentration gradients upstream to locate the source, moving through chemical landscapes that we cannot perceive. To a shark, The ocean is full of invisible trails and clouds of scent, a world rendered in chemical signatures that tell stories about what has passed and where things are. While smell allows long-distance detection, sharks also possess a lateral line system that detects water movements and pressure changes. This system, a line of specialized cells running along each side of the body, senses vibrations and disturbances in the water, allowing sharks to detect struggling fish, swimming animals, or obstacles even in complete darkness or murky water. The lateral line essentially allows the shark to feel objects at a distance, perceiving through water's movement patterns, creating a sense that has no equivalent in terrestrial animals. Combined with other senses, the lateral line helps the shark build a complete picture of its surroundings, multiple sensory streams integrating into unified awareness. The shark's vision, often underestimated, is actually quite good in most species. Sharks have eyes adapted to low light conditions, containing a reflective layer behind the retina called the tapetum lucidum that bounces light back through photoreceptor cells, giving them a second chance to capture photons. This mirror-like layer is what causes sharks' eyes to appear to glow when caught in light. The reflection of that light bouncing back, the enhanced light-gathering ability, allows sharks to see in the dim light of deep water or murky shallows, environments where most creatures would struggle to see at all. Some sharks can also see color, though whether they use color vision in meaningful ways remains uncertain. The underwater world often appearing in limited color palettes as depth absorbs most wavelengths except blue. Not all sharks share the same sensory capabilities equally. Some species emphasize certain senses over others, depending on their lifestyle and habitat. Deep-sea sharks living in perpetual darkness rely heavily on electroreception and smell, their eyes small or degenerate. Sharks hunting in clear open water may rely more on vision, using speed and sight to chase fast-moving prey. Bottom-dwelling species use their lateral line and electroreception extensively, detecting buried prey through the sand. Each species has evolved a sensory suite matched to its particular needs. The same basic toolkit emphasized or de-emphasized to create specialists adapted to particular ways of living. Among the most intriguing aspects of shark biology is their skin, which, as mentioned earlier, is covered in dermal denticles. These structures are not merely protective, but are living tissues that are continuously maintained and replaced throughout the shark's life. The denticles grow from the skin in patterns specific to each species, creating textures ranging from fine and smooth feeling to rough as sandpaper. The pattern and shape of denticles can be used to identify species, each having its characteristic skin texture, like a fingerprint. Some sharks have specialized denticles in certain body regions, rougher textures on leading edges to reduce drag, smoother areas elsewhere, demonstrating that even within a single individual, skin is regionally specialized. This remarkable skin provides multiple benefits beyond streamlining. The rough texture discourages parasites and fouling organisms that might attempt to attach to the shark's body, the denticles creating an unstable surface difficult to colonize. The skin also provides some protection from injury, the overlapping denticles forming flexible armor that can resist scrapes and bites. When sharks interact aggressively with each other, particularly during mating, the rough skin can cause abrasions, and female sharks often show scarring from mating encounters. Though these wounds typically heal without complication, the skin is simultaneously tool, armor, and habitat manager, multiple functions integrated into a single tissue system. Beyond skin, shark teeth represent another remarkable feature, replaced continuously throughout life in a conveyor belt system where new teeth form in rows behind functional teeth, moving forward to replace any that are lost. A single shark may go through thousands of teeth in its lifetime, each one used until it wears out or breaks loose, then replaced by the tooth behind it, moving into position. This continuous replacement ensures that sharks always have sharp, functional teeth, regardless of wear and damage. The teeth themselves vary dramatically between species, each shape suited to particular prey and feeding methods. Some are triangular and serrated for cutting. Others are pointed for grasping. Still others are flat for crushing shellfish. The tooth tells you what the shark eats. Form following function in ways that make perfect sense once explained. While teeth are designed for feeding, sharks also have other specialized structures adapted to their lifestyles. Some species have modified dorsal fins with spines that provide defense against predators. The spines, sometimes carrying mild venom that creates pain and swelling if a predator attempts to swallow the shark. Bottom-dwelling species often have flattened bodies that allow them to rest on the seafloor with minimal exposure, blending into their surroundings. Open ocean species have bodies built for speed, every aspect of their form contributing to hydrodynamic efficiency. The diversity of shark body forms reflects the diversity of marine habitats and lifestyles. Evolution, creating specialists for every niche where a cartilaginous fish might make a living. The various body forms also reflect different strategies for remaining inconspicuous in the ocean. Many sharks are counter-shaded, darker on top and lighter on bottom, a coloration pattern that provides camouflage by counteracting the effects of overhead light. When viewed from above, the dark upper surface blends with the dark depths below. When viewed from below, the light belly blends with the bright surface where sunlight penetrates. This simple color pattern breaks up the shark's outline, making it less visible to both prey and potential predators, allowing the shark to approach undetected or remain unnoticed. The camouflage is passive, requiring no active color change, yet effective in the three-dimensional environment of the ocean, where threats and opportunities can appear from any direction. Some sharks take camouflage further, with patterns of spots, stripes, or other markings that help them blend with particular habitats. Wobbegongs, bottom-dwelling sharks of the Pacific, have elaborate patterns of mottled browns and greens that make them virtually invisible against coral and rocky reefs. Their bodies are flattened and adorned with skin flaps around the head that break up their outline further, making them resemble patches of algae-covered rock more than fish. They lie motionless for hours, waiting for small fish or invertebrates to come within striking distance. Their patience and camouflage, allowing them to ambush prey without needing to chase it actively. The wobbegong has traded swimming speed for invisibility, becoming a living trap that fish swim into without recognizing the danger until too late. While wobbegongs wait motionless, other sharks travel vast distances across ocean basins, undertaking migrations that rival those of any marine animal. Blue sharks, slender, elegant creatures of the open ocean, migrate thousands of kilometers each year, following prey concentrations and favorable water temperatures. Great white sharks travel between feeding areas and what appear to be mating grounds. Individuals tracked by satellite tags showing journeys across entire oceans. Whale sharks, despite their size, move between distant feeding grounds and aggregation sites, their movements likely timed to seasonal patterns of plankton abundance. These migrations represent incredible navigational achievements. Sharks, finding their way across featureless ocean using cues we are only beginning to understand. Magnetic fields, sun position, ocean currents, perhaps even smell. The navigation abilities of sharks suggest cognitive capacities more sophisticated than traditionally attributed to fish. Sharks must remember locations of productive feeding areas, recognize seasonal patterns, and navigate back to specific sites after months of travel. Some sharks show sight fidelity, returning to the same locations year after year, suggesting memory that spans long periods. Young sharks appear to learn migration routes from their mothers or from other adults. Cultural transmission of information that requires social learning and memory. The shark is not wandering randomly but traveling with purpose between known destinations, carrying mental maps of ocean geography that guide their movements across distances that dwarf the sizes of their bodies. While some sharks migrate across oceans, others remain in relatively small home ranges, inhabiting the same reef or stretch of coast for their entire lives. These resident sharks defend territories, establish dominance hierarchies, and develop detailed knowledge of their local environment. They know every cave and crevice, every place where prey hides, every current pattern that brings food or carries scent. This local knowledge allows them to exploit their territories efficiently, finding food and shelter with minimal wasted effort. The resident shark becomes an expert on its small patch of ocean, its survival depending not on ranging widely but on knowing intimately the space it occupies. Not all sharks are strictly solitary. Some species form aggregations, sometimes consisting of hundreds or even thousands of individuals gathered in areas where food is abundant or conditions are favorable. These aggregations are typically not coordinated groups like schools of fish, but rather loose collections of individuals drawn to the same resources, each shark pursuing its own interests while tolerating proximity to others. Within these aggregations, social hierarchies often develop, larger individuals dominating smaller ones, males establishing pecking orders through displays and occasional brief conflicts. These social structures reduce actual fighting by establishing who defers to whom, allowing sharks to coexist in concentrated numbers without constant aggression. Beyond temporary feeding aggregations, some shark species show evidence of more stable social bonds. Female lemon sharks appear to form friendships, preferring to spend time with particular individuals rather than associating randomly with whichever sharks are nearby. These preferences persist across years, suggesting genuine social relationships rather than mere proximity. Young sharks sometimes travel in groups, remaining together as they mature, possibly gaining safety from numbers or learning from each other. The social lives of sharks remain poorly understood, most species being difficult to observe continuously in the wild, but accumulating evidence suggests that at least some sharks have richer social lives than previously recognized. While social lives vary, all sharks must eventually reproduce, passing their genes to the next generation. Unlike most fish, which release eggs and sperm into the water and provide no parental care, sharks use internal fertilization, males possessing paired reproductive organs called claspers that transfer sperm directly to females. This internal fertilization allows sharks to produce fewer, larger, more developed offspring, investing heavily in each one rather than producing thousands of tiny eggs that receive no care. The reproductive strategy shifts from quantity toward quality. Shark embryos developing for months inside their mothers, or in protective egg cases, emerging as relatively large juveniles, capable of fending for themselves immediately. The three main reproductive strategies that sharks employ reflect different balances between safety and resource investment. Oviparous sharks lay eggs in leathery cases that attach to rocks or seaweed, the embryos developing inside the cases over weeks or months before hatching. These egg cases, sometimes called mermaid's purses, provide protection while allowing the developing shark access to oxygen in the surrounding water. Viviparous sharks give birth to live young that develop inside the mother, connected by placental structures similar to those in mammals, the mother providing nutrients and oxygen throughout development. Ovoviviparous sharks hold eggs inside their bodies, where the young develop without placental connections, hatching internally before being born as live juveniles. Each strategy works. Each has advantages and disadvantages, and sharks have explored all three different species, adopting different approaches. The gestation periods for live-bearing sharks are among the longest in the animal kingdom, some species carrying their young for over a year before giving birth. This extended development produces large, well-developed pups capable of swimming, feeding, and avoiding predators from birth. The pups receive no parental care after birth, the mother swimming away and leaving her young to fend for themselves, but the long gestation gives them the size and skills to survive independently. This lack of parental care means young sharks must be fully competent at birth, instincts and abilities pre-programmed by genetics, everything they need to survive, coded into nervous systems that mature before they ever see the open ocean. Young sharks face high mortality, many falling prey to predators, including larger sharks during their vulnerable early period. Those that survive grow slowly, most shark species taking years to reach maturity. some taking decades. This slow growth and delayed reproduction means shark populations cannot recover quickly from overfishing or other sources of mortality. Their reproductive rate insufficient to compensate for elevated death rates. A species that may live 40 or 50 years but does not reproduce until age 15 cannot quickly rebound when populations decline. The biological reality of slow life history, creating vulnerability to rapid exploitation. This vulnerability connects to the modern challenges sharks face. Their ancient, successful strategies becoming liabilities in oceans, altered by human activity. The habitats where sharks live span the full range of marine environments, from shallow tropical reefs to the open ocean, from kelp forests to the deep sea, from frigid polar waters to warm lagoons. Each habitat hosts shark species adapted to its particular conditions, creating a diversity of sharks that fills nearly every aquatic niche imaginable. Shallow coral reefs host small reef sharks that navigate through complex three-dimensional structures, hunting small fish and invertebrates in the maze of coral. Open oceans host fast-swimming pelagic sharks that pursue schools of fish across vast, featureless expanses. Rocky temperate coasts host bottom-dwelling species that hunt among kelp forests and boulder fields. Deep trenches host bizarre, slow-moving sharks, adapted to crushing pressures and permanent darkness. Among the most specialized habitats are the deep-sea realms where pressure is immense, food is scarce, and darkness is absolute. Deep-sea sharks have evolved remarkable adaptations to these extreme conditions, including bioluminescence in some species, light-producing organs that glow in the darkness, possibly for communication or prey attraction. The cookie-cutter shark, a small deep-water species, produces light along its belly, except for a dark collar, creating a silhouette that resembles a small fish from below, potentially attracting larger predators, that the cookie cutter then takes a circular bite from before swimming away. The lantern sharks, another deep-sea group, possess light-producing organs, whose patterns may help individuals recognize their own species in the darkness. In the deep sea, where sight is limited, any light becomes communication. While deep-sea sharks face perpetual darkness, shallow water sharks experience the full cycle of day and night, and many species adjust their behavior according to light levels. Some sharks are primarily nocturnal, resting during the day and hunting at night when their prey is more active or less able to see them approaching. Others are diurnal, active during daylight when vision is most useful. Still others are crepuscular, most active during twilight periods of dawn and dusk when light levels create optimal conditions for detecting prey while remaining relatively inconspicuous. These activity patterns align with prey behavior and competition, each shark species finding its temporal niche just as it finds its spatial and ecological niches. The rhythms of shark life, whether daily or seasonal, create patterns that persist across generations, behaviors timed to environmental cycles that have been reliable for millions of years. Sharks breed when conditions favor offspring survival, migrate when food availability shifts with seasons, aggregate when prey concentrates in predictable locations. These patterns represent evolutionary wisdom, strategies refined across countless generations, each shark following programs written in genetics and modified by experience. The shark is simultaneously ancient and contemporary, carrying patterns from deep evolutionary time while living flexibly in the present moment, adapting within broad constraints to the particular circumstances it encounters. These adaptations, accumulating across millions of years of evolutionary refinement, have created animals supremely fitted to their environments, capable of thriving in conditions that would challenge most other creatures. The shark's success lies not in aggression or ferocity, but in efficiency, in bodies that move through water with minimal waste, in senses that extract maximum information from their surroundings, in reproductive strategies that ensure at least some offspring survive to continue the lineage. They are not monsters to be feared, but marvels to be appreciated. Creatures that have solved the challenges of aquatic existence with elegant simplicity, beings that have persisted while most other ancient lineages vanished. survivors whose presence in modern oceans connects us to eras when the world was fundamentally different, yet somehow familiar. The shark's survival across geological ages provides lessons in resilience and adaptation. Their persistence through changing conditions, demonstrating flexibility within a stable basic design. When oceans warmed or cooled, when sea levels rose or fell, when continents drifted and ocean currents shifted, sharks adjusted, finding new ways to make the old body plan work in new circumstances. Some lineages went extinct, unable to adapt quickly enough, but others survived, and from these survivors came new diversity, evolution, filling empty niches with sharks suited to exploit them. The shark family tree is not a simple line but a branching structure, diversification and extinction balanced across time. The overall pattern, one of persistence through change rather than resistance to it. This evolutionary flexibility manifests in the remarkable diversity of modern sharks, with over 500 described species varying enormously in size, shape, ecology, and behavior. The smallest sharks are barely larger than a human hand, the dwarf lantern shark reaching maximum lengths of around 20 centimeters. A tiny predator of the deep sea feeding on small invertebrates and fish. The largest sharks, the whale shark and basking shark, reach lengths exceeding 12 meters and weights of many tons, gentle giants that filter tiny prey from vast volumes of water. Between these extremes exists every intermediate size, species filling every available niche where a cartilaginous predator or filter feeder might survive. The variation in body form is equally impressive. Some sharks are elongated and eel-like, writhing through crevices and burrowing in sediment. Others are dorsoventrally flattened like rays, though sharks and rays are distinct groups, despite superficial similarities in some species. Still others are robust and torpedo-shaped, built for speed and power in open water. The thresher shark possesses a tail nearly as long as its body, using this elongated appendage to stun fish with whip-like strikes. The hammerhead shark has a head expanded laterally into a hammer or shovel shape, the unusual structure spreading sensory organs across a wider area and possibly providing hydrodynamic advantages. Each form solves particular problems. Each represents an evolutionary experiment in what can be done with the basic shark template. Among the most unusual sharks are the saw sharks, which possess long, flat snouts edged with tooth-like projections, creating a saw that the shark uses to detect and disable prey buried in sediment. The saw is both sensory organ and weapon, covered with electroreceptors that detect buried prey, then swung side to side to stun or injure creatures the shark then consumes. This specialized feeding method works well in particular habitats, the saw shark becoming a specialist in extracting hidden prey that other predators might miss. The specialization limits where saw sharks can thrive, but gives them reduced competition in the niches they occupy. A trade-off between flexibility and efficiency. While saw sharks hunt buried prey, bamboo sharks and epaulet sharks have evolved to walk, using their pectoral and pelvic fins like legs to move across the seafloor or even out of water when necessary. These small, shallow water sharks inhabit tide pools and coral reefs, where walking ability allows them to move between isolated pools as tides recede, accessing food resources unavailable to less mobile species. The walking appears awkward compared to swimming, but is effective. These sharks, navigating through complex rocky environments where swimming would be impossible. Evolution has taken the shark body plan and modified it for terrestrial locomotion, creating fish that can leave the water temporarily, expanding the range of conditions sharks can tolerate. Beyond these physical adaptations, sharks have evolved diverse feeding strategies that span the range from active hunting to passive filtering. Some sharks are pursuit predators, chasing down fast-swimming fish in open water, their speed and agility allowing them to catch prey that tries to flee. Others are ambush predators, lying in wait for prey to approach within striking distance, then lunging with surprising speed from concealment. Still others are scavengers, feeding on dead animals that sink to the sea floor, using their keen sense of smell to locate carcasses from considerable distances. Filter feeders swim through plankton-rich waters with mouths open, straining tiny prey from the water column. Each strategy works in particular contexts, and sharks have explored them all, diversifying into roles throughout marine food webs. The diet of sharks is equally diverse, spanning nearly everything the ocean offers. Some sharks eat primarily fish, others prefer squid and octopus. Still others specialize in crustaceans or mollusks. Horn sharks feed heavily on sea urchins, crushing the spiny creatures with their strong jaws and specialized teeth. Tiger sharks are generalists, eating fish, rays, sea turtles, seabirds, marine mammals, and occasionally garbage. Their willingness to consume nearly anything, earning them a reputation as the ocean's trash collectors. Cookie-cutter sharks take circular plugs of flesh from much larger animals, including whales, dolphins, and large fish, feeding parasitically without killing their hosts. Each dietary preference shapes the shark's ecology and behavior. What the shark eats, determining where it lives, and how it spends its time. This leads to something even more remarkable about how sharks regulate their body temperature. Most sharks are ectothermic, their body temperature matching the surrounding water. But several species have evolved regional endothermy, the ability to warm certain body parts above ambient temperature. The great white shark maintains its swimming muscles, stomach, and brain at temperatures significantly warmer than the surrounding water, using a heat exchange system where warm blood leaving these organs passes close to cold blood, returning from the gills, transferring heat and retaining it within the body. This warming enhances muscle performance and digestive efficiency, giving these sharks advantages in cold waters, where purely ectothermic sharks would be sluggish. The trait has evolved independently in several shark lineages, demonstrating that warming provides sufficient benefits to be worth the metabolic costs. While some sharks warm their bodies, all sharks must manage their salt and water balance, maintaining internal chemistry despite living in seawater that would dehydrate most organisms. Sharks retain high levels of urea in their blood, raising their blood's salt concentration to nearly match seawater, reducing the osmotic gradient that would otherwise cause water loss. This urea retention, combined with specialized rectal glands that excrete excess salt, allows sharks to maintain proper hydration without needing to drink seawater actively. The solution is biochemically unusual, few other animals tolerating such high urea concentrations. But it works for sharks, allowing them to inhabit salt water without the constant battle against dehydration that other marine vertebrates face. Beyond osmoregulation, sharks must also manage their metabolism, balancing energy intake from food against the costs of swimming, growing, and reproducing. Different species have different metabolic rates depending on their activity levels and lifestyles. Active open ocean sharks have high metabolic rates requiring frequent feeding to support their energy demands. Sluggish bottom-dwelling sharks have lower metabolic rates, able to survive on less frequent meals, sometimes going weeks between feedings. The metabolic strategy matches the shark's ecology. Fast swimmers paying high costs but catching mobile prey, while slow-moving species conserve energy but must hunt less active or sessile prey. Evolution optimizes the balance, each species finding the metabolic rate that works for its particular way of making a living. While metabolism determines energy needs, feeding behavior determines how those needs are met. Many sharks feed opportunistically, taking whatever suitable prey they encounter, rather than specializing on particular species. This flexibility allows them to persist when preferred prey becomes scarce, switching to alternatives rather than starving. Other sharks are specialists, focusing on particular prey types and becoming highly efficient at catching them. Hammerhead sharks hunt stingrays buried in sand, using their broad heads to detect electrical fields and then pinning the ray while biting. Blue sharks specialize on squid, their slender bodies and long pectoral fins suited for maneuvering through open water where squid congregate. Each strategy has advantages, generalists finding food more reliably, but specialists feeding more efficiently when their prey is available. The feeding process itself varies by prey type and shark species. Sharks that feed on fish often use suction, rapidly expanding their mouths to create negative pressure that draws prey in before jaws close and teeth grip. Sharks feeding on large prey use their powerful jaws and sharp teeth to bite and tear, sometimes removing chunks of flesh from animals too large to consume whole. Sharks feeding on hard-shelled prey may use crushing bites, their teeth adapted to break shells rather than pierce flesh. Filter-feeding sharks use their gill rakers, comb-like structures that trap small prey while water passes through. Each feeding method reflects the shark's diet, form and function, aligned through evolution to create efficient feeding machines suited to particular prey. While feeding occupies much of a shark's time and energy, sharks also rest, though their rest looks different from terrestrial animal rest. As mentioned, many sharks must swim continuously to breathe, so their rest involves reduced activity rather than complete stillness. Swimming slows to minimum speeds necessary for respiration, the shark gliding more than actively propelling itself, conserving energy while maintaining basic functions. Brain activity during these rest periods shows patterns suggesting sleep, though whether sharks experience anything like the unconsciousness that accompanies mammalian sleep remains unknown. They rest with eyes open, maintaining some awareness of surroundings, ready to respond to threats or opportunities even while resting. Not all sharks rest on the same schedule. Some are active throughout day and night, with brief rest periods interspersed, while others show clear daily rhythms with longer periods of rest during particular times. These patterns often align with prey behavior, sharks resting when prey is unavailable or difficult to catch, becoming active when feeding opportunities improve. The flexibility in rest schedules demonstrates sharks' ability to adjust behavior to match circumstances, not locked into rigid patterns but responding adaptively to the conditions they encounter. The shark rests when resting serves it, hunts when hunting is productive. Flexibility in daily scheduling being one of many ways sharks optimize their energy budgets. Beyond daily patterns, sharks experience seasonal changes in behavior, activity, and physiology. In temperate and polar waters, water temperature varies dramatically between seasons, and sharks adjust accordingly. Some migrate to warmer waters as winter approaches, avoiding the coldest periods in areas where they would become sluggish and vulnerable. Others remain but reduce activity, their metabolism slowing with temperature, requiring less food and moving less frequently. Reproductive cycles often follow seasonal patterns, females giving birth or laying eggs when conditions favor offspring survival. Timing that requires internal tracking of seasons and readiness to breed at appropriate times. The shark is embedded in seasonal rhythms that structure its year, patterns repeated annually, connecting each year to those before in predictable cycles. While seasons change predictably, individual circumstances vary, and sharks show behavioral flexibility in responding to unexpected conditions. When prey is unusually abundant, sharks may gorge themselves, storing energy for leaner times. When conditions become unfavorable in their usual habitat, they may move to new areas, exploring and potentially finding better conditions. When injured, they reduce activity and find sheltered locations where healing can occur with minimal energy expenditure. This behavioral plasticity complements the physiological and morphological adaptations that suit sharks to their environments, allowing responses to circumstances that genetics alone cannot anticipate. Among the most impressive demonstrations of shark learning ability are studies showing that sharks can be trained to respond to signals, associate stimuli with rewards, and remember learned information for months or years. Captive sharks learn to recognize feeders, to come when called, to navigate mazes, and to discriminate between objects based on color or shape. Wild sharks learn locations where food can be found reliably, remember individual humans who feed them, and modify hunting strategies based on experience with what works and what does not. This learning capacity indicates cognitive flexibility and memory that enhance survival, allowing sharks to improve their performance through experience rather than relying solely on instinctive behaviors. The social learning that appears in some shark species adds another layer to their cognitive abilities. Young sharks that observe adults feeding in particular ways may adopt those techniques, cultural transmission of hunting methods that spreads through populations without genetic change. Sharks that associate with others may learn to avoid areas where companions have had negative experiences. Indirect learning that allows benefit from others' mistakes. These social learning abilities require not just individual intelligence but social awareness, recognition that others' behavior contains useful information, attention to what others are doing and outcomes they achieve. The social sharks become smarter than solitary ones could be, collective knowledge exceeding what any individual discovers alone. While intelligence serves sharks well, they also rely on instincts programmed by evolution, behaviors that emerge without learning, because they have been successful for so many generations that they have become genetically encoded. Newborn sharks instinctively swim, hunt prey of appropriate size, avoid predators, and respond to environmental cues that guide them towards suitable habitat. These instincts provide a foundation that learning builds upon, basic competencies that keep young sharks alive long enough to acquire the learned knowledge that will serve them throughout life. The balance between instinct and learning varies between species, with some relying more heavily on pre-programmed behaviors while others depend more on flexibility and learning. Beyond individual intelligence and instinct, sharks must navigate the social landscape of other sharks. Interactions that can be cooperative, competitive, or neutral. When sharks aggregate at food sources, dominance hierarchies often establish who feeds first and who must wait. These hierarchies reducing conflict by clarifying relationships. Larger individuals typically dominate smaller ones, and males often dominate females outside breeding contexts. The hierarchies are maintained through displays and occasional brief conflicts, sharks establishing and reinforcing rank without excessive fighting. These social structures allow multiple sharks to coexist in limited space, sharing resources according to rules that reduce the costs of competition. During breeding season, social interactions intensify as males compete for access to females and females assess potential mates. Male sharks may compete through displays, showing off their size and condition, or through physical contests, biting and pushing rivals. Females choose mates based on size, health, or dominance status, selecting males whose quality suggests good genes for offspring. The courtship may be brief, encounters lasting minutes, or extended, pairs remaining together for hours or days. After mating, males and females typically separate, the brief union serving its reproductive purpose before the sharks resume their solitary or loosely social lives. There is no pair bonding or long-term partnership, each shark pursuing its own interests once reproduction has occurred. The pregnant female now faces months of gestation, her body sustaining, developing embryos while also maintaining her own metabolism and continuing to feed and avoid predators. The energetic demands of pregnancy are substantial, the female needing to find and consume enough food to support both herself and her growing young. In some species, pregnant females may alter their diet, seeking more nutritious prey or feeding more frequently. They may also change their behavior, becoming more cautious to avoid injury that might harm developing embryos, or selecting different habitats where food is more abundant or predators less common. The pregnancy transforms the female's life, redirecting resources and attention toward reproduction, investment that will culminate in birth and the beginning of a new generation. When birth finally occurs, it may happen in shallow, protected nursery areas where young sharks are safer from predators, or in open ocean where the female happens to be when gestation completes. The pups emerge ready for independent life, swimming away immediately, following instincts that guide them toward appropriate habitat and food. The mother provides no care after birth, may even pose a threat to her offspring if hungry. The young sharks needing to distance themselves quickly from all larger sharks, including their own mother. This lack of parental care places enormous pressure on young sharks to be competent immediately, their survival depending entirely on the instincts and abilities they possess at birth. Young sharks face numerous dangers in their early life. Larger sharks, including adults of their own species, will eat them if given the chance. Other predators, including large fish, seals, and dolphins, also hunt young sharks. The risk is highest in the first weeks and months of life, when the young sharks are smallest and least experienced. Many do not survive their first year, falling prey to predators or failing to find adequate food. Those that do survive this vulnerable period grow steadily, their size providing increasing protection as they become too large for most predators to handle easily. Growth rates vary between species, some growing quickly and reaching relative safety within a year or two, others growing slowly and remaining vulnerable for longer periods. As young sharks grow, they gradually expand their range and capabilities. They venture into deeper water, tackle larger prey, begin exploring beyond the nursery areas where they spent their early months. This expansion is gradual, the shark testing boundaries and learning the larger world incrementally, building confidence and skill through successful experiences. Eventually, they leave nursery areas entirely, joining the adult population in habitat that may be quite different from where they grew up. This ontogenetic habitat shift is common in sharks, young and adults often living in different places and eating different prey, reducing competition between generations and allowing both to thrive without directly interfering with each other. The transition from juvenile to adult is gradual rather than sudden, sharks slowly acquiring the size, experience, and reproductive maturity that defines adulthood. The timeline varies enormously between species. Some small sharks maturing within a few years, while large species may take a decade or longer to reach reproductive maturity. This extended period of immaturity serves multiple purposes, allowing time for growth to sizes where reproduction becomes energetically feasible, time for learning and experience accumulation, and time for survival testing before genes pass to offspring. Only sharks with sufficient genetic quality and behavioral competence survive long enough to reproduce. Natural selection occurring continuously as individuals face the challenges of finding food, avoiding predators, and navigating their environment. Once mature, sharks may reproduce multiple times across their remaining life, though reproductive frequency varies between species. Some sharks breed annually, while others breed every 2 or 3 years, the interval allowing females to recover body condition lost during pregnancy before attempting reproduction again. Males may be capable of breeding more frequently since their investment per reproductive event is lower, though they still expend energy courting and mating. The reproductive lifespan can span decades in long-lived species, individuals potentially contributing to many generations of offspring, their genetic legacy spreading through the population as their young survive and reproduce in turn. While reproduction continues the species, individual sharks eventually age and die, their bodies returning nutrients to the ocean ecosystem. Aging in sharks remains poorly understood, some species apparently living decades or even centuries, though determining age is challenging because sharks lack hard structures that record annual growth rings like those found in fish scales or ear bones. Some methods use vertebral growth bands, counting layers that may represent annual increments, but these methods are imprecise and difficult to apply to many species. The Greenland shark, a slow-moving species of Arctic waters, may live for 400 years or more, making it possibly the longest-lived vertebrate on Earth, though confirming such extreme longevity is challenging with current methods. The death of a shark creates opportunities for scavengers and decomposers, the body's nutrients recycled through the food web. In shallow water, the carcass may be quickly consumed by scavengers, including other sharks, crabs, and various fish. In deep water, the carcass may support specialized communities, similar to whale falls, slow decomposition, feeding organisms adapted to scarce food resources. The shark's death is not an ending but a transformation. Matter and energy, reorganizing into new forms. The atoms that comprise the shark, dispersing and becoming parts of other organisms, continuity through change, rather than cessation. While individual sharks die, the species persist, populations maintaining themselves through the balance of births and deaths, the collective surviving even as individuals come and go. This population-level persistence has allowed sharks to continue for hundreds of millions of years, their overall success transcending the limited lives of individuals. The population is not merely a collection of sharks, but an entity with its own dynamics, responding to environmental conditions, evolving over time, adapted at a level beyond the individual. Understanding shark conservation requires thinking at this population level, recognizing that protecting individuals matters primarily because it maintains populations, which are what actually persist across evolutionary time. The populations of many shark species now face serious challenges from human activities, primarily from overfishing that removes sharks faster than reproduction can replace them. Sharks' slow growth and late maturity make them particularly vulnerable to overfishing. Populations declining rapidly when fishing pressure is high. Commercial fisheries target sharks for meat, fins, liver oil, and cartilage, demand creating fishing pressure that many populations cannot sustain. Bycatch, where sharks are caught unintentionally in fisheries targeting other species, adds to direct fishing mortality. The combined pressure from targeted fishing and bycatch has reduced many shark populations to fractions of their historical sizes. Some species now considered endangered or critically endangered. The impact of shark population declines extends beyond the sharks themselves, affecting entire ecosystems through processes called trophic cascades. As top predators, sharks influence populations of their prey, which in turn affect species lower in the food web. When sharks are removed, their prey may increase dramatically, overgrazing their own food sources and creating ecosystem imbalances. In some Caribbean reefs, shark declines have allowed prey fish populations to explode. These herbivorous fish overgrazing algae that compete with coral, inadvertently benefiting coral health. In other systems, shark removal has caused predator-prey fish to increase. These predators then reducing populations of herbivores, allowing algae to overgrow and smother coral. The cascading effects can be complex and system-specific, but they demonstrate that sharks play important roles in maintaining ecosystem balance. Beyond ecosystem impacts, shark declines represent losses of biodiversity, each species' extinction, removing millions of years of evolutionary history and unique genetic information. The species that go extinct are not interchangeable with others, but represent distinct lineages with their own adaptations and ecological roles. Once extinct, they cannot be recreated. Their particular solutions to survival challenges lost permanently. The accumulating extinctions impoverish the biosphere, reducing the variety of life forms and the resilience that diversity provides. Protecting sharks is thus not merely about preserving particular species, but about maintaining the overall richness and complexity of life on Earth. While the challenges facing sharks are serious, conservation efforts are increasingly addressing these threats through various approaches. Some countries have established shark sanctuaries, large areas where shark fishing is prohibited, allowing populations to recover in protected waters. Fishing regulations, including catch limits, size restrictions, and gear requirements, aim to reduce fishing mortality to sustainable levels. International agreements regulate trade in endangered shark species, attempting to reduce market demand that drives fishing pressure. Marine protected areas provide refuges where sharks can feed, breed, and grow without human interference. These conservation measures show promise where implemented effectively, demonstrating that shark populations can recover when threats are reduced. Public awareness campaigns have also shifted attitudes toward sharks, countering the negative stereotypes that have long characterized these animals as dangerous monsters. education about shark biology and ecology, media coverage highlighting their vulnerability rather than their threat, and ecotourism that allows people to observe sharks safely, have all contributed to more positive views. As public opinion shifts toward valuing and protecting sharks, political support for conservation measures increases, creating conditions where effective regulations can be implemented and enforced. The cultural change complements legal and management approaches, all components working together toward the goal of ensuring shark populations persist into the future. Among the most effective arguments for shark conservation is the economic value that living sharks provide through ecotourism. In locations where sharks are abundant and accessible, tourism focused on observing sharks generates substantial revenue, often exceeding the value that dead sharks would provide through fishing. Divers pay to see sharks in their natural habitat, supporting local economies through tourism spending on accommodation, food, guides, and transportation. This economic argument for conservation appeals to interests beyond pure environmental protection, creating financial incentives for maintaining shark populations. When sharks are worth more alive than dead, communities have reason to protect them, conservation becoming economically rational rather than merely ethically desirable. The ecotourism approach works particularly well with large charismatic species that attract diver interest. Whale sharks, basking sharks, hammerheads, and even great white sharks draw tourists willing to pay significant amounts for opportunities to observe these magnificent creatures. The tourism is not without concerns, as excessive numbers of boats and divers can disturb sharks and alter their behavior. But when managed appropriately, it provides conservation benefits, while allowing people to experience the wonder of encountering sharks in the wild. These encounters often transform participants' attitudes, fear and misunderstanding, replaced by appreciation and respect. Personal experience creating conservation advocates, who then support protection measures. While ecotourism provides economic value, sharks also provide less tangible but equally important benefits through their ecological roles and their contribution to the ocean's health. Healthy shark populations indicate healthy ecosystems, their presence signaling that food webs remain intact and that the ocean can still support top predators. Protecting sharks thus serves as umbrella conservation. Protecting sharks requires protecting their prey, their habitat, and the overall ecosystem functions that sustain them. The sharks become indicators and ambassadors, their well-being reflecting broader ocean health, their conservation benefiting many other species that share their environment. Beyond their ecological importance, sharks hold value simply as remarkable products of evolution, beings whose existence enriches the biosphere, regardless of any utility they provide to humans or ecosystems. They have intrinsic worth as living creatures with their own interests and experiences, entities that matter to themselves, even if they matter to no one else. This intrinsic value creates moral obligations to protect them, to ensure that human activities do not drive them to extinction, to share the planet with other forms of life that have as much right to exist as we do. The argument for shark conservation can be made on ecological, economic, and ethical grounds, all perspectives supporting the conclusion that protecting sharks is worthwhile and necessary. As conservation efforts continue, research into shark biology and ecology provides the knowledge base necessary for effective management. Scientists track shark movements using satellite tags, revealing migration routes and critical habitats that need protection. Genetic studies examine population structure and diversity, identifying distinct populations that require separate management. Reproductive studies determine age at maturity and reproductive rates, information essential for calculating sustainable fishing limits. Dietary studies reveal what sharks eat and how they fit into food webs, knowledge that helps predict ecosystem consequences of population changes. Each research study adds to the foundation of understanding that supports conservation decisions, turning protection from guesswork into science-based management. The accumulated knowledge reveals sharks to be far more complex and vulnerable than stereotypes suggest. They are not mindless eating machines, but intelligent animals with sophisticated senses, elaborate behaviors, and important ecological roles. They are not infinitely resilient, but slow reproducing species vulnerable to overexploitation. They are not monsters to fear, but creatures that typically avoid humans, their presence posing minimal actual danger to people. As knowledge replaces mythology, public perception shifts, creating conditions where effective conservation becomes possible. The shark is being reimagined from villain to valued member of ocean ecosystems, from threat to treasure worth protecting. While much has been learned about sharks, much remains unknown, particularly about deep-sea species and populations in remote locations. New species continue being discovered, particularly small deep-water sharks that have escaped notice due to their inaccessibility. Known species reveal unexpected behaviors or capabilities as observation technology improves and study effort increases. Migration routes surprise researchers as tracked sharks travel to unexpected locations. The shark remains partly mysterious, not fully documented or understood, still capable of surprising those who study them. This ongoing discovery keeps shark research vibrant, each answered question generating new questions, ensuring that future generations will have mysteries to solve. Among the mysteries that researchers continue exploring is the question of shark cognition and subjective experience. Do sharks feel pain, fear, contentment? Do they have preferences beyond simple stimulus response patterns? Can they plan future actions, or merely react to present circumstances? These questions resist easy answers because we cannot directly access another creature's inner life, cannot know what existence feels like from inside a shark's brain. We observe behavior and measure physiological responses, inferring mental states from external signs. But the actual quality of shark consciousness remains private, inaccessible to observation. The shark experiences its life in ways we can only guess at. Its subjective world, hidden behind behaviors we can document, but never fully understand. While inner experience remains mysterious, outward behavior reveals that sharks engage with their world in complex ways that suggest genuine awareness and responsiveness. Sharks explore novel objects, approaching cautiously and investigating with multiple senses before determining whether something is food, threat, or irrelevant. They modify behavior based on experience, learning from success and failure in ways that suggest memory and planning. They respond differently to different individuals, recognizing familiar sharks or humans and adjusting their approach accordingly. These behaviors indicate processing beyond simple reflexes, the shark evaluating circumstances and choosing responses based on some form of understanding rather than automatic programming. The shark's relationship with its environment is not passive but active, the shark shaping and being shaped by the ecological context it inhabits. Through feeding, sharks influence prey populations and indirectly affect species throughout the food web. Through their movements, they transport nutrients between different areas, connecting distant ecosystems through their migrations. Through their waste, they fertilize the waters they swim through, recycling nutrients and making them available to phytoplankton that form the base of oceanic food webs. The shark is not separate from the ecosystem but embedded within it, a node in vast networks of interaction that span the ocean, influence, and being influenced by countless other species in ways both obvious and subtle. Beyond ecological interactions, sharks engage in relationships with other species that range from parasitic to mutualistic. Remoras, fish with modified dorsal fins that work as suction discs, attach to sharks and hitchhike, feeding on scraps from the shark's meals and parasites on the shark's skin. The shark may benefit from the cleaning or may simply tolerate the remora's presence, the relationship being commensal, if not truly mutualistic. Pilotfish swim near sharks, possibly gaining protection from the shark's presence, while providing no clear benefit to the shark. Various parasites including copepods, worms, and protozoans live on or in sharks, extracting resources while providing nothing in return. These interspecies relationships add layers to shark ecology, each shark existing not alone but accompanied by diverse organisms that depend on it or exploit it. While parasites and commensals associate with individual sharks, cleaner fish establish stations where sharks visit to have parasites removed, a mutualistic interaction where both participants benefit. The shark receives cleaning service, reducing parasite loads and keeping skin healthy, while cleaner fish receive food in the form of the parasites they remove. These cleaning stations become important features in some habitats, places sharks visit regularly, creating predictable patterns that researchers can use to observe and study sharks that might otherwise be difficult to encounter consistently. The cleaning interactions represent cooperation between species, mutual benefit arising from behaviors that serve both parties' interests. Not all interspecies interactions are beneficial. Sharks face threats from several marine predators, including other larger sharks, orcas, and occasionally large crocodiles in estuarine environments. Orcas have been documented hunting several shark species, sometimes targeting specific body parts like livers while leaving the rest of the carcass. These predation events, while rare, remind us that sharks are not invulnerable, that even apex predators face dangers from species capable of overcoming their defenses. The presence of predators shapes shark behavior, creating landscapes of fear where sharks avoid areas or times when dangerous predators are likely to be present. Beyond natural predators, human activities pose the greatest threats to most shark populations. Fishing, as mentioned earlier, directly removes sharks from the ocean faster than reproduction can replace them. Habitat degradation destroys the coastal nursery areas and coral reefs where many sharks feed and reproduce. Climate change warms waters, acidifies oceans, and disrupts food webs in ways that cascade through ecosystems to affect sharks. Pollution introduces toxins that accumulate in shark tissues, potentially affecting health and reproduction. These threats operate at multiple scales, from local habitat loss to global climate change, creating pressures that challenge shark populations worldwide. Among the most insidious threats is the practice of shark finning, where sharks are caught, their fins removed, and their bodies discarded back into the ocean to die. The fins are valuable in certain markets for use in soup and traditional medicine, while the bodies are less valuable and take up space on fishing vessels. This wasteful practice is now banned in many jurisdictions, but enforcement is challenging, and finning continues in areas where regulations are weak or absent. The practice is particularly damaging because it kills large numbers of sharks for minimal actual use of the animal. Waste compounding the tragedy of population decline. While some fishing is wasteful, even well-managed fisheries create challenges for sharks whose life history makes sustainable harvest difficult. Determining sustainable catch rates requires accurate information about population size, reproductive rates, natural mortality, and growth rates, data that is often incomplete or entirely lacking for many shark species. Without this information, managers must make conservative estimates to avoid overfishing. But political and economic pressures often push for higher catch limits than biology can sustain. The result is that many supposedly managed shark fisheries have led to population declines, sustainable use proving difficult to achieve in practice, even when theoretically possible. The challenge of managing shark fisheries is complicated by the fact that sharks often migrate across international boundaries, populations shared between countries with different regulations and enforcement capabilities. A shark population protected in one nation's waters may be heavily fished when it migrates into another country's waters, the protection in one area being undermined by exploitation in another. Effective conservation requires international cooperation, agreements that span political boundaries and bind nations to compatible management regimes. Such cooperation is difficult to achieve and maintain, competing interests and priorities creating friction that slows progress toward effective protection. Despite these challenges, progress continues as more countries recognize the importance of shark conservation and implement protective measures. The number of shark sanctuaries has grown, covering increasingly large areas where sharks receive protection from fishing. More species are added to international trade agreements that regulate commerce in shark products, reducing market demand that drives fishing pressure. Fishing regulations become more common and more sophisticated, incorporating the best available science into management decisions. These positive trends give reason for cautious optimism, suggesting that the trajectory of shark conservation, while still concerning, is at least moving in the right direction. While governments and organizations work on conservation policy and management, individuals can contribute to shark conservation through their choices and actions. Consumers can avoid purchasing shark products, reducing market demand that drives fishing. Recreational divers can support responsible ecotourism that generates value from living sharks while minimizing disturbance. Citizens can support organizations working on shark conservation through donations and volunteer work. Voters can support political candidates who prioritize environmental protection and science-based management. These individual actions, multiplied across many people, create the political and economic conditions that allow effective conservation measures to be implemented and sustained. Beyond direct conservation actions, spreading accurate information about sharks helps counter the fear and misunderstanding that have long hindered protection efforts. When people understand that sharks are not monsters but fascinating animals facing serious threats, they are more likely to support conservation. When people recognize the ecological importance of sharks and the ecosystem services they provide, protection becomes more compelling. When people appreciate the beauty and grace of sharks through documentaries and personal encounters, emotional connections form that motivate conservation support. Education and outreach are thus essential components of conservation strategy, changing hearts and minds in ways that enable the policy changes necessary for effective protection. As conservation efforts continue, they operate against a background of ongoing research that constantly revises our understanding of sharks. New tracking technologies reveal previously unknown movements and behaviors. Genetic analyses uncover hidden diversity and population structure. Physiological studies explain how sharks accomplish remarkable feats of diving, thermoregulation, and sensory perception. Each discovery adds nuance to our picture of shark biology and ecology, replacing simple narratives with complex realities, mystery yielding gradually to understanding, while new mysteries emerge to replace those solved. Among recent discoveries are findings that some shark species may live far longer than previously thought, implications for population dynamics and conservation, requiring reassessment when sharks take decades longer to mature than earlier estimates suggested. Other research has revealed unexpected intelligence and learning abilities, sharks solving problems and showing social awareness that challenges assumptions about fish cognition. Still, other studies have documented sharks using tools. One species observed picking up and manipulating objects to achieve goals, behavior traditionally considered evidence of advanced intelligence. Each finding expands our appreciation for what sharks are and what they are capable of, their complexity becoming more apparent as study intensifies. While scientific understanding advances, cultural attitudes toward sharks continue evolving, popular media slowly shifting from portraying sharks as villains to presenting more balanced and accurate depictions. Documentaries showcase shark diversity and behavior, revealing gentle giants alongside efficient predators, emphasizing wonder over fear. Films and books increasingly portray sharks sympathetically, as creatures worthy of protection rather than elimination. Social media spreads images and videos of sharks in contexts that highlight their beauty and vulnerability, creating viral moments that shift public opinion. These cultural changes complement scientific and policy developments, all components working together toward a future where sharks are valued and protected rather than feared and persecuted. The path toward that future is not guaranteed but remains possible, conditional on choices being made now and in coming years. Shark populations can recover if fishing pressure is reduced and critical habitats are protected. Ecosystems can regain balance when sharks are allowed to fulfill their ecological roles. The wonder and mystery that sharks represent can persist for future generations, if current generations commit to conservation. The outcome depends on collective will, on whether humanity chooses to share the ocean with these ancient mariners, or allows them to slide toward extinction through indifference or short-term thinking. While the future remains uncertain, the present still contains sharks. Their presence in the world's oceans, a gift we have inherited from deep time. Each shark swimming through the sea is a miracle of evolution. 400 million years of refinement expressed in streamlined form. They embody persistence, having survived catastrophes that eliminated most other lineages, demonstrating resilience through adaptation and flexibility. They represent mystery. Much of their biology and behavior still unknown, their inner lives inaccessible to human understanding. They inspire wonder, creatures so perfectly adapted to their element that they seem to merge with the ocean itself, becoming liquid motion, consciousness dissolved in blue. To encounter a shark in the wild is to glimpse something ancient and other. To see a form of life that evolved along paths so different from our own that connection seems impossible yet somehow exists. We are both animals, both products of evolution, both experiencing existence in our particular ways. The shark does not know we exist, does not ponder the strangeness of air-breathing apes, watching from boats and beaches, simply continues being shark, pursuing the same imperatives its ancestors pursued when our ancestors were still small mammals hiding from dinosaurs. There is something humbling in this. Recognition that we are newcomers to a world that sharks have inhabited for durations we struggle to comprehend. The shark's ancient lineage connects present to distant past, but sharks also project forward, their future extending as far ahead as we allow. The sharks alive today may be ancestors of sharks that swim oceans we cannot imagine, in worlds shaped by processes we cannot predict, adapting to conditions we cannot foresee. Or they may be among the last of their kind, terminal generations, watching lineages end, 400 million years of success, culminating in extinction, caused by a species that arose only moments ago in evolutionary time. Which future becomes real depends on choices, on values, on whether we decide that a world with sharks is worth preserving. As these thoughts drift through your mind, imagine the shark gliding through dark water, its form barely visible, a shadow among shadows. It moves with purpose known only to itself, following currents of water and instinct toward destinations it does not question. The shark does not worry about its future, does not mourn its endangered status, does not contemplate the strangeness of existence. It simply exists, being shark, doing what sharks do, living the life that evolution and circumstance have given it. There is purity in this, existence without reflection, being without becoming, presence without past or future, just the eternal now of movement through water. The shark's simplicity is deceptive, its apparent thoughtlessness belying the complexity of its senses, the sophistication of its adaptations, the long history encoded in its genes. Behind the streamlined exterior exists nervous system and sensory organs of remarkable capability, processing information and generating behaviors that have kept sharks successful across eras when countless other species failed. The shark is simultaneously simple and complex, ancient and contemporary, powerful and vulnerable, predator and prey, monster and marvel, fear and wonder. It contains multitudes, meaning shifting with perspective, each angle of viewing, revealing different truths. And now the sharks fade behind your thoughts, sinking into the blue depths where they spend their quiet lives. We have drifted through 100 gentle truths about these misunderstood creatures, from their ancient origins spanning 400 million years to their remarkable senses that detect electricity and vibration, from their efficient streamlined bodies to their surprising intelligence and learning abilities, from their gentle filter-feeding giants to their diverse forms, adapted to every ocean habitat. You are connected to this world. You share this planet with sharks, your existence overlapping theirs in this moment of Earth's long history. You are both animals, both expressions of life's creativity, both temporary arrangements of matter experiencing existence. The same ocean that holds sharks covers most of the planet you inhabit. The same sun warms both air and water. The same evolutionary processes that created sharks also created you. Though the paths diverged hundreds of millions of years ago, life exploring different possibilities, taking different forms, arriving at shark and human through separate journeys from common origins. Tonight, as you rest, sharks continue their endless gliding through the world's ocean. In warm tropical waters, reef sharks patrol coral gardens, searching for sleeping fish, their movements graceful and unhurried. In cold temperate seas, basking sharks filter plankton from the water column, mouths agape as they drift through clouds of microscopic life. In the deep ocean, bioluminescent sharks produce their own light in the darkness, glowing softly as they search for prey in the eternal night of the abyss. In shallow coastal nurseries, young sharks grow and learn, preparing for the lives they will lead in the vast blue spaces beyond. The sharks continue, as they have continued for longer than mountains have stood, longer than continents have held their current shapes, longer than humans have walked upright. They persist because they are superbly suited to their environment, because they are flexible with instability, because they are survivors, and you are safe, warm, resting in the knowledge that the ocean still holds sharks, that these ancient mariners still patrol the depths, that mystery and wonder persist in a world that sometimes seems fully known. They swim through darkness and light, through warm and cold, through all the oceans that cover this blue world, living their quiet lives far from shore, bothering no one, asking nothing except the space to exist. They are patient as the tide, ancient as stone, gentle despite reputation, survivors of ages beyond counting, teachers of adaptation and persistence, reminders that life takes forms beyond our imagining and succeeds through strategies we are only beginning to understand. If you are still awake, go ahead and watch the next chapter. Sleep well and dream softly of streamlined forms gliding through blue water, of senses detecting invisible fields, of ancient lineages persisting across geological ages, of creatures neither good nor evil, but simply alive, moving through their element with grace, earned across deep time. At home in depths we can visit only briefly, belonging to the ocean in ways we can only observe and wonder at. Good night.